Hello, everyone. Welcome to section 2.8. This section is on one-to-one functions and their inverses. There's a lot of material in this section, so I recommend you put on your thinking caps because we're going to go on a journey here. Okay, so to start off, let's talk about one-to-oneness. So function f is called one-to-one if no two elements of the domain, it's the domain of f, have the same output. So in symbols, what that means is, so that is so every time you have two inputs that aren't the same, so you've got an input x1 and an input x2, then their outputs aren't going to be the same. So that's what being one-to-one means. In pictures, because usually this is easier to see on a graph, and it's usually actually easier to see what's going on if we look at something that's not one-to-one first. So if we do something maybe like this, and if we look at like x1, we go up here, we see it hits there, right? It hits here at this value, right? So this is f of x1. But notice that if we come over here, there's another point that also goes to that height, right? This x2. So this is also f of x2. But the problem here is that x1 and x2 are different. So we have this, but x1 or f of x1 is the same as f of x2. So this right here, this one is not one-to-one. Okay, but let's see a picture of something that is one-to-one. It might look something perhaps like, I don't know, like this. Okay, so now if you were to take any point, like this x1, and you go up here, and then it's going to be at this height right here, so this is f of x1. And then if you take any other point, like maybe pick randomly here, this is x2, you go up here, you go across, we see it is at a different height, has a different output. So this one is one-to-one. Okay. All right. So this kind of gives us a hint as to what kind of like test or method we can use to like look at a graph of a function and decide if it's one-to-one or not. So that test is called the horizontal line test. And this probably is sparking some memories because it sounds very much like the vertical line test. And yeah, it's the exact same kind of test, except this time, instead of using a vertical line and scanning across, we're going to use a horizontal line. We're going to scan top and bottom. Okay, so the rule is as follows. If a horizontal line crosses the graph of a function more than once, that function is not one-to-one. Probably make that better. See, there we go. So if you have a horizontal line and it happens to cross the graph more than once, then it's not a one-to-one function. It's kind of the same idea as the vertical line test, where we had a vertical line, and if it crossed the graph more than once, it wasn't a function. This is, we have a horizontal line, crosses the graph more than once, it's not 1 to 1. So let's see maybe some examples of that. So let's say we've got the graph x-axis or y-axis, and maybe it looks something like maybe like a cubic polynomial here. So degree 3 polynomial, maybe something like that. And then if we look at a horizontal line and we start at the bottom and we move our way up, we're good. We're good here. We're good here. And then bam, oof. Suddenly, if we look at this horizontal line here, we happen to cross not only at more than one point, we cross at 3 different points. So crosses at 3 points. That one, that one, that one. And so this one is not 1 to 1. Okay. Let's see another example. Let's get our axes. And maybe let's do something like, let's do like the square root function. So that looks like this. Now, if we take a horizontal line and we start at the bottom and we kind of go up and we see we're good, we're only crossing 1 point, only crossing 1 point, only crossing 1 point, and it's gonna stay that way. So this one, we never get to a point where we can draw a horizontal line and cross the graph more than one. So this one is indeed 1 to 1. Okay, excellent. But how can we decide if a function is 1 to 1 based off of the equation? So that's the question. How do we decide if a function is 1 to 1 by its equation? So to do this, you have to kind of, first you have to guess whether it's going to be 1 to 1 or not 1 to 1, because there's 2 different methods for checking each of those cases. So we're going to go with, first, we're going to look at how to show f is not 1 to 1. So to show some function f is not 1 to 1, here are the steps. First, right here, we'll actually make it a number. First, you pick an x1 and x2. So you have to pick 2 inputs where x1 does not equal x2. So you need to pick 2 specific numbers that you can plug into the function such that you can show that f x1 is equal to f of x2. By plugging them in. So you need to pick 2 specific numbers that you can plug into the function, 2 different numbers. You plug them both in, and if you show that the function spits out the same number for those 2, then it's not 1 to 1, because it doesn't uphold the definition. So let's see an example of this process. So let's say we want to show f of x equals x squared is not 1, 2, 1. So for our first step, we're going to pick, and the choice of which numbers you pick for this is really up to you. For this problem, I think I'm going to pick x1 equals 1 and x1 equals -1. And yeah, there's a little bit of like experience and just practice that goes into deciding like what numbers are going to work out for you. and it helps to kind of understand the basic shape of the function. So this is just an x squared. It's relatively simple. I kind of know what it looks like, and so I kind of know what values are going to work out. So this is just a case where it's like you just got to do a couple problems and get familiar with it, and then it'll start becoming easier to kind of pick which points will work out for you. Okay, so we picked those 2 points, and now we're going to plug them into the function, and we're going to see what happens. So if we do, let's do f of x1 is, we're going to plug in 1, right? And so if we plug in 1, we get 1 squared, which is just 1. But now if we look over here and we plug in x2, so that'll be f of -1. We plug in -1, and that becomes squared, and -1 times -1 is just 1. So so x1 does not equal x2, right? Because 1 does not equal -1. But not by. But f of x1 does not equal f of x2 because, or sorry, it does equal it, my bad. That is, f of -1 is equal to f of 1. So f is not 1 to 1. Okay. So that was trying to show f is not 1 to 1. But what if we look at a function and we're like, we think this is 1 to 1. Well, how do we show that? So to show f is 1 to 1, here are the steps you take. First, you start with arbitrary x1, x2, okay? And by arbitrary, I mean you're going to leave them as variables, okay? So don't pick specific numbers for these. We want to just leave it as x1, x2, because that way, if we show that it's 1 to 1 for x1, x2, because they were arbitrary, they were random, we never actually picked them, it shows it for like any choice of those two, okay? So don't pick specific numbers. Leave as variables. Okay, and then what you're going to do is start with the assumption that f of x1 equals f of x2. Okay, so you're going to start with this equality. You're going to start with this equation, and then from there you want to show x1 equals x2, and that will show 1 to 1. So that seemed like a weird and convoluted process. Let's see it in action. So let's show f of x equals x cubed plus 1 is 1 to 1. So our first step was start with 2 arbitrary variables. So we're going to consider x1 and x2. Okay. So remember, they're arbitrary. All right. Next, we assume f of x1 equals f of x2. And since f here is x cubed plus 1, that means that we've got x1 cubed plus 1 equals x2 cubed plus 1. And now the third step is solve. So we're going to take this. So we've got x1 cubed plus 1 equals x2 cubed plus 1. I'm going to subtract 1 from both sides. And so we get x1 cubed equals x2 cubed. And then I'm going to cube root both sides. So, and then we get x1 equals x2. There's no plus or minus because we did cube root, not a square root. So, and that's exactly what we wanted to show. So f is 1 to 1. Cool. Okay. But why do we care about 1 to 1 functions? Like, what's so special about them? Well, here's the thing. It has to do with our next topic, inverses. So if a function is 1 to 1, then, well, here, let's give this function a specific name. Make some room for it. So if a function f is 1 to 1, then f has an inverse. Similarly, if f has an inverse, f is 1 to 1. And you have me being, wait, hold on. Inverse, what exactly do you mean by that? Well, so let's see, yeah, the definition of that. So we'll let f be a function. We'll let it be a 1 to 1 function. The inverse of f, and usually this is denoted, call it, it's denoted by f inverse like that. So f, and then like a superscript -1. A way to think about it is it goes backwards to f. So if f of x equals y, f inverse of y equals x. So if f sends like a point x to a point y, f inverse is going to be the arrow going backwards along that route, okay? And inverses are nice because if you have an inverse to a function, you can undo it. So you can start talking about the reverse of certain processes. So inverses can be very useful both in modeling, but also in a lot of other mathematics. So, but how do we find them, right? That's the tricky part. So steps to finding inverses. And some of you are probably already familiar with this process, but if you aren't, that's okay. So first we're going to write as y equals f of x. And what I mean by that will become clear in a minute when I do an example. And then you're going to solve for x if possible. Sometimes it's not fully possible to solve for x, and then the inverse is pretty hard to find. But solve for x if you can, and then 3, swap out the x's and y's. So let's see an example of this. So let's find the inverse of, we'll do f of x equals, and then we'll do, let's do the square root of x plus 2. So remember, our first step up here was write out as y equals f of x. And so what that's going to mean for us is we're going to write y equals square root of x plus 2. Okay. Now the second step is to solve for y. So for this second step, first I'm going to square both sides. And so we get y squared equals x plus 2. And then I'm going to subtract 2 from both sides. And so we get y squared minus 2 equals x. And then now I've solved for x. And so the third step says to swap x and y. And so we get x squared minus 2 equals y. And so the final answer would be f inverse of x equals x squared minus 2. Excellent. Okay. But sometimes these things can get pretty tricky. So let's see another example of that. So let's do find the inverse of, and we'll do g of x equals, let's do a rational function, 2x plus 3 over x minus 1. So first off, we need to write y equals g of x. So that's going to be y equals 2x plus 3 over x minus 1. And now we want to solve for x. So we start with this. And now what I'm going to do is I'm going to multiply both sides by x minus 1. Okay. And so what that's going to do is it's going to cancel the denominator, and we're going to get x minus 1, y equals 2x plus 3. And now what I'm going to do is I'm going to distribute the y into the parentheses. And so we get x, y minus y equals 2x plus 3. And now I'm going to do some fancy footwork here, and you'll see why. So I'm going to add y to both sides, and I'm also going to subtract 2x from both sides. And so what that gets you is you get xy minus 2x equals y plus 3. And the reason I wanted to do that is now all the x terms are on one side together, and all the terms that don't have an x in them are on the other side, which means that I can take these x's because they're in every term, and I can pull them out. So now you get x times y minus 2 equals y plus 3. And now I'm going to divide both sides by y minus 2. So we get x equals, because these cancel, and we get y plus 3 over y minus 2. And thus we've solved for x. And so then the third step is to flip the x and y. So we get y equals x plus 3, x minus 2. And so g inverse of x is x plus 3 over x minus 2. All right. Excellent. There's one more thing that we need to do with inverses, and that's looking at them graphically. So finding inverses graphically. So if we start with a graph, if you have a graph of a one-to-one function, then the inverse, or the graph of the inverse, is the original graph. Reflected about the y equals x line. So that was a lot of words. Let's see what that means in pictures. So if we've got our coordinate grid, and let's say we've got a function that maybe looks like, I don't know, maybe like this. So let's say this is f of x. And the y equals x line is this diagonal line right here. This is y equals x. Now, if you imagine that the yellow dotted line that I just drew is like a mirror, and what you're going to do is you're going to flip the line, or sorry, flip f along the line. So it's like looking at its reflection in a mirror. And so it would probably start out here, and it would go in and back out. Oops. Kind of back in again a little bit. See, there we go. And so this would be f inverse of x. So you can kind of see how they're symmetric about this dotted yellow line, right? So that's how we find inverses graphically. So if we want to see that again, the different function, so x, y, I'm going to go ahead and just draw the dotted line in first. So we're going to need it anyway. And let's say that f of x maybe looks something like, you know, like a scaled square root or something. So something maybe like this. Now it crosses the line, the yellow dotted line, but that's fine. So now if you imagine reflecting it, it's going to go like this. So this would be f inverse of x. All right, and that's finding inverses with graphs. So we covered a lot of ground today. We started talking about one-to-one functions and how to deal with those, the horizontal line test, finding ways to prove things are one-to-one or not one-to-one. And then we talked about inverses because those two topics are very closely tied. And we talked about finding inverses and finding the graphs of inverses. So take time to digest all that. That was a lot of material. Keep working on the homework, hone your skills, take care of yourselves, and of course, let me know if you have any questions whatsoever.